Okay, so I'm Shane Henderson. I'm going to do a pale imitation of an introduction compared to Sid. So don't get your hopes up. But basically, this is Raaz. Raaz is going to join Cornell Tech as an assistant professor in January. Until then, he's officially visiting assistant professor, but he's an assistant professor in ORIE. He has a lot of different skills that he brings to bear on personalized healthcare decision making, and I guess also personalized decisions more broadly. But you'll see that in a second. He's drawing on all kinds of skills. Berkeley PhD, he did a postdoc that was joint between Harvard and MIT, and you know Wards. He's good. Okay.
As Shane said, I will be here for this month and a little bit of next month. And today I want to present to you some of the things that I'm very excited about recently. And this is, of course, most of the work is through my postdoc, a bit from my PhD, but the research threads are very active, in my mind at least. So the title is, in my opinion, a catchy one, but so the talk has two parts, and I don't expect to actually go through the second part because I'm in no longer the job talk pressure. So I'll take it slightly easy on my own. And so so the two parts deal with the two different applications. One is about simulating heartbeats at a user level. So that's like where you're trying to do personalized prediction of heartbeats for a given user. That's what the personalization there is. And the second part is about a clinical trial that was called HeartSteps. There it was about nudging users to walk more so that they can have a healthier lifestyle. And the clinical trial was called HeartSteps. So just trying to, and there the trial was trying to personalize these nudges to the users. So it was again about personalized decision making. And in general, I'm very excited about this field that has kind of now become central to many different disciplines, where you're trying to use data and models to make decisions that are personalized to different users, their preferences, their historical data, instead of using one-size-fits-them-all kinds of decisions or rules. And this is being driven by the extensive amount of data that is being collected through different sensors, for example, your cell phones or trackers like Fitbits and Apple Watches, and the computation has become more affordable, and also the rise of interdisciplinary research, that you bring ideas together from different fields, OR, applied math, statistics, computer science, and that is what makes this a very exciting field. Ideally, to make decisions that are tailored to different users or units, what you would like to see or simulate is the future under different possible decisions. And if you could simulate the future, you take the best action. But to simulate, you would need models, right? Once you have models, you run simulations and you observe some data. And that's what I call you're using simulations to predict decisions effect and doing decision making. Well, to do this, given a model, there are different abstract or mathematical tasks that you'd like to do. For example, optimization. Like once you have a model and you want to tailor it to a particular user, you have to quickly optimize to fit the model to user needs. Of course, the models will not be perfect because they are built over time, and there will be uncertainty in the parameters, so you want to do this uncertainty quantification in a rigorous manner and hopefully quickly enough. And then, of course, in some tasks, you have to also propagate uncertainty to some downstream final task, not just at the model level. And that's what the part one of the talk today will be about, is how to quickly propagate uncertainty in a computational cardiology application. And just as a disclaimer, I did not directly work on this application. It was a collaboration of my collaborators. So it was like in two hops. And it just serves as a very nice motivation for the kind of challenges we are trying to tackle in this direction. So in this direction, I'm assuming somebody gave me the model. But of course, models are built over time using lots of real data and domain science. And that is the direction I call that you're using real data to build a model, or in simple words, string infer decisions effect. And there are different kinds of data sets nowadays that you would like to use, ranging from observational data, that is like health records that are out there, or running trials, clinical trials, or more like there is now this wave of running sequential trials where you're using reinforcement learning to do sequential decision making and do give interventions to a user multiple times. And in this direction, the task is, given these data sets, you want to understand whether the decisions are effective or not at a personal level. And I call that direction inference. And time permitting, I'll give you some overall results and the setting in part 2 of the talk in a mobile health application. Okay? All right. So with that, let's dive and make things more concrete for the talk. Yeah, so simulations, I mean, I guess in applied math department, you don't have to motivate too much of that these simulations are not trivial, and these are very complicated, often multi-scale, but just to bring everybody on the same page, by multi-scale I mean you're trying to simulate some, say, heartbeats at the heart level. So you think of heart as the system, that's the organ, and you think of different sub-components or sub-modules as smaller units. So the basic unit is the cell, so you do some modeling here, then you do some modeling at the tissue scale, and you put the pieces together to get the overall heart model. And similar analogies you can think of in aerospace, or even nowadays in self-driving simulation platforms where you model what is going on, how a pedestrian behaves, how a car driver behaves, how they interact, and then how a full-blown simulation would look like. And actually, there are these applications where, again, this kind of analogy will show up. And the reason for me to show this is we'll focus on this level, but you can see that similar ideas would be useful across other applications. Okay, so the particular application we are thinking about is simulating heartbeats in a cardiology application. And in particular, people are interested in understanding how some issues or some dysregulation in calcium signaling, that is a cell level event, affects irregularities in heartbeats at the heart level and cause arrhythmia, which can be lethal in some cases. So how things going wrong here affect things going wrong at the heart level. And in particular, in more concretely, the goal is to, the way they want to understand this is by building simulation models that they are called digital twins. And digital twin means it's a computational model which is supposed to be twin for a given user's heart. So it's a personalized model, and you want to simulate those models to understand if things go wrong here, what happens at the heart level. The eventual goal of these kind of simulations is, of course, to run personalized clinical trials in simulations so that you don't have to run it on human beings. You know, that's the downstream gold standard goal in the future, but this is one building block towards that. So to do that, a classical or a common approach is to put some models. So there is some differential equation model, 38-dimensional differential equation model that characterizes calcium signaling. And then you try to, it has some parameters that you have to tailor to different users. So you take some measurements on some single cells, and then you do some inference, typically via Bayesian setup, to estimate these parameters. But because you're only doing finite number of measurements, you also quantify uncertainty using a posterior distribution. And to quantify uncertainty, you'll use something like sampling, Monte Carlo sampling. So that is cell level phenomena. And then, because you are not certain about how things are happening here for a given user, you propagate uncertainty by sampling these cell model configurations and propagating it to a whole heart simulator. So you run many simulations of the heart for different configurations of the cell model for a given user to understand how uncertainty here affects the fluctuations or the predictions at the heartbeat level. Yes?
Is it important what that whole heart model is? Like if it's a finite element model, for PDE or something else, or doesn't it matter?
So of course, in real life, it does matter. Today, you will see how it would matter for our problem. Okay? Yeah. So, but today we'll abstract this mathematically in the next slide, and then I'll comment a bit on when it matters. So, let's make things more concrete, introduce some notation so that we can talk things more formally of what we're trying to do here. So, denote the cell model by X, and you're trying to capture the uncertainty in X. So you have a posterior, and you're drawing some samples to capture the uncertainty in the knowledge of cell model X. Okay? And in this application, it's a 38-dimensional posterior. So you have 38 parameters that are unknown in the differential equation model. And then to propagate uncertainty, it's like you have Hart model F, and the typical way to do this would be to compute some mean and variance of F under this posterior. Because it's a complicated posterior, you don't have this in closed form, you approximate it using sample mean. So now F is, this F could be a simulator or any arbitrary function that you're interested in. Okay. So that's the typical approach. So both tasks are very standard, like there's nothing fancy going on here. The only challenge is these tasks are computationally challenging. So in uncertainty quantification part, usually T is large. So the number of samples you draw is large because this is a complicated and high dimensional posterior, and you want to make sure that the chain has mixed. So it's very common to have a million or a few million iterations. So T is around 10 to the 6. And that can be challenging, and sorry. Yeah. So in this particular task, it takes around 2 CPU weeks to run such a long chain. Okay. But you can parallelize, and like in practice, it will be like a few hours on a few thousand CPUs. That's how it will be implemented. However, in this task, it's even more challenging to run this F, which is like a finite element methods model, so that a single F evaluation takes 4 CPU weeks. So just this naive sample mean would require you to use 4 million CPU weeks in computation. So you need a lot of CPUs to, of course, you will not wait for 4 million weeks, which I don't know how long that is in years. Like you will use many CPUs to run this, but this is just computationally too hard to do it. So my research tries to tackle these tasks, like how to make MCMC computationally faster, and then today we'll be talking more about how to make this task, which looks daunting, even tractable with some guarantees. Okay? Any questions on the setup? Yes?
You have 38 dimensions, while you only need 1 million samples. That, to me, is already pretty good.
Oh, well, I'm not saying you need only 1 million samples. Okay. It's of the order of millions. And in this application, the data that we'll be using from prior one, they ran the chain for 2 million iterations. And they do some diagnostics to say that it seems to have done well. There are other issues, but I'm not saying it's sufficient. It's kind of like typical. Okay? Yeah. Any other questions? Okay. So, and the idea that we'll be working on today is a simple one. So our goal is to estimate, say, this mean. I cannot evaluate the function t times because t is too large. Well, you can compress the data into a smaller size S and compute sample mean over the smaller data set. And you have fewer evaluations. So, but you need to care that, yes, you will save computation. You need to also care about your accuracy, like what happens to the accuracy. If these t points are IID or are coming from a fast mixing chain, you can easily show that the error between the unknown mean and the sample mean is of the order d to the minus half. This you can think of in Chebyshev, central limit theorem, whatever. That's the standard range. And if you do what is often done in MCMC literature, or what is the first guess at Yeah, and what is typically done is do deterministic thinning, so take every 1000th point, or do just uniform subsampling. Then you can show easily that the error between this sample output, the output mean, would be of the order s to the minus half. So if s is smaller, say in our application, you have to actually think from million to around 1000. So think of s as square root t, then this error is t to the minus quarter. So your error is worse, although you have fewer function evaluations. Yes?
Can you comment on x prime I? How you construct?
Oh yeah, so these are a subset of the original data set. In this talk, these will be the subset. So that's the question, how do you get it? So if you get deterministic subset or uniformly random subset, these are the rates you get.
Because x prime I is the subset of it. It's not
It's-
only one.
So this, I would suppose these are million points.
Yeah.
This is like 1000 points from the million points. Yeah. So we are taking literally the points. Okay. Any other question? So we'll, in the talk, we'll focus on this heavy compression setting. That is, we are going from t to the square root t points. The paper has more general results where there is s here, and the baseline is t to the minus quarter for the typical practice. But we can ask, like, is that the best you can do if you were to do something other fancy thing? And there are like known lower bounds of t to the minus half. So if you're going to compute your output by sample mean over t to the half output points, so that's called the Corset estimator, your rate cannot be better than t to the minus half in the worst case. Or if your input is TIID points, no matter what you do, in the worst case you cannot get better than t to the minus half. Okay? Yes?
The lower bound, is it of the form you tell me what method you are using, there exists an f for which this is true? Or?
So it's more like there exists a p for which there exists a worst case p, that if you have this estimator or you have this input.
And under minimal assumptions on f.
Yeah. Okay. Great. So if you compare with the baseline, you see that there is a gap. This is the same rate as this side, but with fewer evaluations is what this seems to suggest. So there is room. We have to figure out if we can fill the room. Okay. So let's look at what have prior people, like what has prior work done. So fast integration is a very rich literature. There's a lot of methods. Bunch of them fall in this category that do give you faster than t to the minus quarter rate. So I denote it by small o. Like quasi-Monte Carlo is a whole field of itself. Bayesian quadrature methods, or different, this is some work I did during my PhD, then determinant point processes. But they prove these faster error rates under special assumptions on P star. So P star is sometimes known that it is the uniform distribution on unit cube. I'm only interested in integrating functions on this unit cube. In that case, you can get faster rates. And when they try to generalize it, they often assume that the support is bounded. So you are on a bounded domain, compact domain, and the density is bounded away from 0. So it's not exactly uniform, but it is close to being uniform. Or they assume that the function class is special. That is, you are integrating linear functions, or not infinite dimensional functions. Okay. So then they can prove fast rates. And there are a bunch of these methods. Then there are methods that try to go for a more general case, so generic P star, and rich function classes, not finite dimensional function classes. And there are methods like kernel herding, greedy methods, super sampling, support points. There are a bunch of these methods. They often have good empirical performance, but when you try to prove if they get faster than t to the minus quarter rate, the best known results are not better than standard thinning. Okay. So practically they might do fine, okay? But provably we don't know they're fine. Yes.
Sorry, just a notation question. Could you say what you mean by capital O with a tilde on top as opposed to like regular big O?
Yeah, so tilde means it can hide some log factors.
Thank you.
log t.
Okay.
That might depend on d as well, the dimension. Okay, but yeah, hiding log using factors. All right. Any questions? So now we come to the main contribution that we want to discuss in this talk, is that we have a new procedure that is provable and also practical. Like you can deploy it and it works. It's not just a construction that gives you this fast rate t to the minus half. Thanks for asking the tilde question, because this means there are log factors hidden in here. And this applies to generic P star and generic domains. We'll dive in more detail what these rates look like. But it does apply not to just uniform P star or with bounded support. And it applies to rich function classes. We call this method kernel thinning. And we'll unpack what rich function classes mean in the next slide. Okay? So that's the TLDR. If you want to just take away and not understand the technical details, is the baseline. We beat the baseline. This is nearly minimax optimal up to log factors for like the lower bounds apply to us as well, to the level of generality. And that prior work gets you fast rates, but not in this generality, or they show empirical performance but don't have these rates in the generality. Okay. Yes.
So we've been talking about different classes of F, right?
Yes.
Now, so what should I think of F? Would F be an indicator function that
Great.
patient survives or something like that? Is that sort of the...
What F function class? Yeah, great question. So we'll go to the next slide. Like in this talk, what does this function class mean? So this will be a function class in a reproducing kernel Hilbert space. And so that this is our error metric. Worst case integration error in some unit ball of a Hilbert space. Now what is this Hilbert space? It's parameterized by a kernel, and you can think of it as, suppose the kernel is a Gaussian kernel, then the function class is effectively analytic functions that have exponential tails. So that's what the function class is. If you have Matern, B-spline, then you can also think of function class that has tails but only has finite number of derivatives. So that's the, and then you embed them in this kernel space and use this metric to measure the quality. So that's what we are talking about. Fully analytic functions, or also functions with finite amount of smoothness. Okay.
I'm sorry, so tell me, but how does it apply to patient and heart, right? So...
Great. Yeah, so the question would be exactly that these function classes are rich enough. If you choose kernels appropriately, then these function classes are rich enough to provide you uniform convergence. So they are dense in L2 function space. So we won't be able to tell you like which kernel is most appropriate for the heart simulation, because we don't understand the full heart simulator. But what we can say is, based on your understanding, if is the simulator very smooth, or is it very like it has a few derivatives? If it has no derivatives, then there is nothing to be done. So if you are willing to make some smoothness assumptions about the underlying simulator, then you can pick a suitable kernel, and then the rest of the theory will follow. Okay. So your question is a very valid practical question. For a given problem, I have transferred the problem to telling me a kernel. Which kernel do I choose? For that, I don't have a great answer right now. Okay. I'll just say, tell me a little bit about your function class, and I have some kernels to recommend. Okay? Yeah. So this metric for popular infinite dimensional kernel choices also metrises convergence in distribution. In simple words, if this quantity is going down to 0 at a certain rate, that means that the output distribution is converging to the true distribution at that rate. Okay. In distribution, so weakly convergent. So that's why these metrics are commonly used in this literature, because they give you this flexibility, but choosing kernel remains. It's like we have made it another problem. We have given you a solution, converted it into another tricky problem. Okay. But today, our theory will apply to a large class of kernels. So our goal was to develop methods that work for a very large class of kernels. Okay. So I'll try to give you a main result so that it's more formalized, and then describe the algorithm, and we'll come to the results. So the main result is a high probability error bound that says that kernel thinning uses roughly t evaluations of kernel k to output t to the half points that with high probability satisfy the following. So I am assuming here that your input points have this Monte Carlo rate of t to the minus half. If you don't want to assume this, then just think of this quantity as PTF, that is the input mean. Okay. So without that caveat, the error rate is that the true mean minus the output mean is of the order log t by t square root times the norm of the function times square root of the infinity norm of the kernel. And this applies to a fixed function in the RKHS, and this guarantee applies to any kernel. Like, I don't have to make any assumptions about the kernel actually. It even applies to kernel on graphs, something like that. Like, it doesn't have to be a Euclidean space either. So compared to standard thinning, this the rate there was t to the minus half. Here it is t to the minus half. Sorry, it was t to the minus quarter. Here it is t to the minus half.
Just nice question. So f is not a vector value function.
So you can think of it as a vector value, but in the talk is like a real value function. Yeah. I mean, but it does not stop you from. Then you have to think of L2 norm error, not absolute error. Any questions on the bound? Okay. So this is for a fixed function. So to make it worst case error, that depends on the tail behavior of P star and the kernel. So if your P star has sub-Gaussian tails and the kernel has sub-Gaussian tail, for example, with a Gaussian kernel, then the worst case error rate is log to the d by 2 plus 1 by t. Here d is the dimension of the Euclidean, the points, where the points lie. So if d is too large, these rates might not be very appealing. And we'll see whether up to what dimensions can you push, or like see any empirical improvement. If tails get heavier, that is P star has sub-exponential tails and your kernel has sub-exponential tails, then the log factors get worse. This becomes log to the d plus 1 t by t. So up to these log factors, these rates match the minimax t to the minus half error rate. If your P star has heavy tails, then the rates are no longer 1 over root t. They degrade from t to the minus half to t to the minus quarter, depending on how much smoothness there is in the underlying distribution. Yes.
So what is this infinity norm of K? For example, for
Yeah.
Gaussian kernel.
Yeah. So for Gaussian kernel, this would be 1. So this is like e to the minus. So your Gaussian kernel is e to the minus x minus y square by sigma square. So it's the worst case value, which is 1 when x. Yeah. So yeah. Any other question? Yes.
So this requires a linear number of variations, right?
Yes. So
Correct.
this is also a surprising thing. People would typically assume it will require quadratic number of evaluations because you are looking at all your kernel pairwise kernel evaluations, but actually we can bypass it. So it does require linear evaluations of kernel. Yes.
How are you bypassing that?
Oh, that is after the talk.
Okay.
Yeah. I mean, there is a procedure. We have procedure. Yes.
Stupid question. The kernel takes as input what and outputs what? I understand it takes as input two things and outputs a number.
Yeah. So it takes input as the input the points. So kernel is k, x, y. So x and y are your input points. So if for the heart example, these will be the cell models. And k, x, y would be a real number. Okay. Yeah. So you can also think of in one dimension min x comma y is a kernel. Okay. That's another. It's like a Sobel-Merton kernel. Or e to the minus quadratic is a kernel. So people who are familiar with Gaussian processes think of kernel as the covariance functions you are choosing. So depending on what covariance function you use, you get different error rates. Yeah. So that's what is going on. Yes.
So as your kernel gets less and less smooth, as it reduces the baseline case that is purely an integrable function.
Yeah, then you go to t to the minus quarter. That is correct. So this rate degrades from, this is in some sense the best case. There is actually one more. faster rate, just root log t by t when you have compact. So compact, then sub-Gaussian, sub-exponential, and you degrade to t to the minus quarter if they have no assumption. Okay. And just to contextualize, if you remove this p star and put a pt here, that is the input mean on the points, and output has size s, then you should think of this rate as 1 over s instead of 1 over square root s. So that's what is happening. So it's a quadratic improvement. Any question? All right. So let me elaborate what the procedure is, and then we'll go to the results. So the way kernel thinning proceeds, it takes points, and sorry Z, we don't elaborate here what exactly it outputs, but under the hood it's some kernel function. And then the way thinning proceeds is it does recursive halving. So it takes t points, halves them into t by 2 points, then t by 4. If you do it log t times, then you get root t points. And then we have some refinement steps. Okay. So that's the recursive halving to get down to square root size. Okay. So if you want to do a halving to s points, you just stop earlier or later, depending on what your output size you want. So, and the goal in the halving, so I only need to now describe what is halving doing, then and how is that working. So the goal in halving is, you can pretend, suppose the kernel is identity kernel, so that v1 is equal to x1, just for simplicity. Otherwise, just think our goal is now to preserve sample means. So sample mean on this should be close to sample mean on this. So that's what is written here. This is our goal for each halving round. So if you do it log many times, you accumulate this error log many times. Okay. So this is our goal. And the way we do this is by reducing this to a discrepancy minimization problem, which says that given vectors v1 through vt, choose signs plus minus 1 such that epsilon I vi, this sum is small, and then if you have the and output points that have epsilon I equal to minus 1. Okay. So that's the equivalence, and I will give you a two-line proof why these two are equivalent problems. This one and this one. Okay. And the proof is very simple. You just write epsilon I vi, decompose it into two sets of terms, the ones that have plus ones and the ones that have minus 1. I just rewrote it. And you can now add the second term to get the complete sum and subtract it so that you have 2 here with minus sign, right? So I just add and subtract the second term. And now you divide by t, and then you start to see the equivalent. So this green is the sample mean on the input mean, blue is the output mean, and what we want is this error that we want to be small. Okay. So it's a very simple reduction. So that's our goal. So I have reduced that thinning to recursive halving to a sign assignment problem, such that this summation sign epsilon I vi remains small. Okay. So how should we choose epsilons? That's the next question. So you can, the first guess would be, let's just do IID, plus minus 1 with equal probability. You can see quickly, without too much attention, that if you just compute the variance of this term, you're adding Vt square at round t. So you're just constantly adding variance. So that if all the Vt's are constant, after t iterations, this is of order t, so that the fluctuation is of order the standard deviation, so it's square root t. Okay. And this is happening because epsilons are independent and equal probability. It's a good fun problem to work out. And this is what actually happens when you're doing standard halving or standard thinning. Under the hood, the mapping is exactly this. So that's why you have. So now what we do is, how do we make it better? So here we can try to choose epsilons in a correlated manner. So you have a vector epsilon j vj. The next epsilon should be somehow negatively correlated to these epsilon, the sign sum so far. Then if you write the recursion, you will have a negative term here. And you can show that actually now variance satisfy a recursion such that sigma t square is less than beta times the previous variance plus the new term, where beta is less than 1. So here there was equality with beta 1, here it's less than 1. So this behaves like a stable dynamical system, or it's a very it's a stable equation, and if you solve it with the right parameters, the right way to negatively correlate this, choose beta appropriately, then you get that this is actually root log. Ideally, we would like this to be constant, but for now, in the manner we are doing, it's root log t. There are other solutions that get you called a constant order. So if you compare these two, you see this root t to root log t improvement, and that propagates to getting you the fast rates. And this is what kernel thinning is doing. So this idea of discrepancy minimization and choosing these epsilons in a correlated manner is like, these ideas are common in the TCS community, and we are just leveraging one version of that that was introduced like a couple of years ago in Alvis et al.'s work. It was called self-balancing walk, and you can think of kernel thinning or one piece of kernel thinning as a self-balancing Hilbert walk. So we are now doing balancing in the Hilbert space, not in the Euclidean space. So that's the idea. Any questions?
So here the Vj is f of xj, but f has been replaced by a linear combination of the kernel shifted at the random points.
So yeah, so if you want to know what exactly these v's are kx2i dot minus kx2i plus 1 dot. So that you also have exact halving, no matter how you choose it.
Okay, yeah, great.
So it's the difference of two kernel functions centered at pair of points. Yes?
Maybe jumping ahead a bit, I'm guessing you're using the online discrepancy.
Yes.
Why was the extra log t term there? Instead of t?
Because of the you want to control it for t rounds, right?
Yeah.
So your delta becomes delta by t. So we try to optimize it, but it's hard to avoid root log t in the online version. So there is an offline version, like it's called Gram-Schmidt walk. There it's constant, but the runtime. So if you do self-balancing, you get t square runtime, which with another wrapper we brought it down to order t time, which I will not discuss today. So quadratic to linear. Gram-Schmidt walk, which makes this constant 1, that has t to the 4 runtime. We brought it down to t square by our wrapper, but t square is still very slow. Yeah. So we went for an inflation by log factor, and actually in practice, this log factor is not really there because we have a post-processing step, which I didn't discuss in the talk. So, so we are very competitive with the offline version, and I think this is probably not there after our post-processing, but it is there if we don't post-process. Yeah. Thank you. Any other questions? If not, let's visualize the too quick. Well, never mind. I was going to make it slightly slow. So let's just visualize the output, and these are actual runs. Like I didn't just pick the points and just show it. So here we have 8 mixture of Gaussians. So these are denoting the components. We take 64 points, and we do the 2 procedures: standard or uniform thinning and kernel thinning on it with Gaussian. Then you see the output looks different. Like here, you just miss some modes by chance, and that's just the nature of standard thinning. But kernel thinning is a bit more strategic, and it tries to find the points. Note that we are not telling kernel thinning that there are these admixture of Gaussians. Like it just happens under the hood. Okay. Yeah. So it is because you have better approximation of P star, you get better error rates. Okay. Now let's see whether it quantitatively we see such a thing. So this is our first simulation where we know the target is Gaussian P star, so that we can measure the worst case error with a Gaussian kernel. So it's you can numerically evaluate it. So I will show 4 plots. X-axis is the output size, which is root t. So we'll change t, and y-axis is the worst case error, which in this case can be computed. And the input is IID distribution, IID Gaussian in RD. So in d equal to 2, you see that the error rate of kernel thinning is t to the minus half, while for IID points is t to the minus quarter. So if you do standard thinning or uniform thinning of IID points, it is still IID. So it's as if you're doing root TID points. So you get this t to the minus quarter rate. So this is consistent with our theory, but this is just 2-dimension. And one thing that was important to us was to build a solution that also scales and has some nice property in high dimension, because oftentimes these integration methods, because of those hideous log factors, don't really work in high dimensions. So let's see if it actually works for our method in high dimensions, or if you think this is high. So there's D4, D10, D100, and you see that the rates get worse, this t to the minus half, t to the minus 0.48, and that is because of the log factors. But what was surprising actually is that if you, the x-axis looks, or powers of 2, but its power of 2 to the 3 is just 8. So what we are showing here is that in 100 dimensions, even with 8 points, you see a statistical gap between these error rates, which was kind of pretty surprising. Like, we thought these would be matching for a while and then they will start to separate, but that was not the case. All right. So now let's go back to the simulator example and what we did here. So in this case, we don't really know the true posterior. So what we did was, but we know the input distribution of the chain because we have the points. So from prior work, we took 2 MCMC runs on 2 different posteriors, and we tried to thin using Gaussian kernel. So now the worst case error on the y-axis is to the input distribution, not the underlying posterior, which we don't know. So the first result looks somewhat like this. So this is a 38-dimensional process or experiment. So here you see that actually the red points or the standard thinning is already pretty good. It's t to the minus 0.46, not t to the minus quarter. And we can discuss why that is the case. So standard thinning is already doing good, but kernel thinning provides you improvement in error rates as well as in magnitude. And that actually happens across the 4 runs, or like the 4 chains. So the gap does not look that impressive, but it is actually like meaningful in this problem, because if you fix an error threshold, it's as if you need only half the output points. And in this example, 50% computational savings is non-trivial because each point is worth 4 CPU weeks. So if you originally intended to use 1,000 CPUs, now you can get away with 500 CPUs. Okay, and this also shows why real world is harder than simulations in general. Like, to get a real gain it's not easy. Any questions? If not, then that was the that summarizes the part 1 of the talk, which is we were looking at compression to speed up integration and uncertainty propagation by using some embedding in kernel spaces. And this, I didn't get to the linear time part of it, but just to give you a sense of how quick, what's the current state of affairs. So if you want to thin 100,000 points in 100 dimension, it takes around 10 minutes. And it's now even faster, but 10 minutes is a good proxy. One thing I didn't mention is that we are compressing the input points. So if the input points are incorrect, that is, they are not the right sample from the distribution you care about, we inherit that bottleneck. Like, our guarantees truly apply between the input mean minus the output mean. So if the input mean is wrong, we are wrong. So, and that actually happens in this MCMC example. So how to fix that bias? So that's an ongoing work. We are trying to make our work compatible and how to fix the bias. But here you need to know a bit more about the posterior distribution. Like, currently we were assuming access only to samples. But to fix the bias, you need to be able to estimate the bias. For that, you need to know something more about the distribution, otherwise it's hard. And this compression idea, you can use it for other tasks. So we were focused on integration, but we have recently finished this work where you can compress the data sets and do hypothesis testing, where you use kernel methods to do testing between whether 2 sets of samples are equal or are there some features that are independent. Then the naive runtime of prior procedures is quadratic in input size, so it takes a few hours. And if you do this compression to square root n size, then it takes like a few seconds. And we show that we can speed up from hours to seconds without really losing the accuracy, which in this case means power. And then this is currently we are working on this, or like we have started work on it. Like, what if you want to do ERM, and if Hilbert makes progress through the semester, we may have something to say about this sooner or later. So this is the library. We call it good points because we're trying to find good points. And currently we have 3 algorithms, kernel thinning. So the kernel thinning itself has the best accuracy, but it takes n squared time. We speed it up with a wrapper called compress++, so it reduces the runtime. It makes the error 4 times worse, not more, just a factor of 4. But it makes the runtime very fast. So this is the one I was citing the runtime of. And you can use the compress++ to speed up other thinning procedures as well. Like, it's a nice wrapper. And then this is something I didn't talk about, which is compress and test, which provides you fast speedups while giving input guarantees. Okay, so now we have around 10-15 minutes, and I can give you a quick overview of the other HeartSteps problem, and then we can stop there. Does that make sense? Or Shane, yes.
Sounds great.
Yeah.
But 2 quick questions.
Yeah.
So with plain old Monte Carlo, you get this free error estimate. Can
You
you
mean
get
Sigma F, right? Yeah, yeah.
Can you get free error estimates?
That's another project working on it.
And the other question is, with some of the fancy quasi Monte Carlo schemes, you get really nice speedups for smooth integrands.
Yeah, like you mean even better than
Much
t
faster.
squared, t cubed, yeah, yeah,
Much better.
yeah.
Can something similar to that happen here?
Not in the current version, no. Because I think they're really hammering on the underlying distribution, which we are not. So I think we have to do something more. Yeah. Because if you know your target distribution is Gaussian, then with a Gaussian kernel you can get exponential in t, e to the minus t error rates. But it's very tight. So yeah. So no, this procedure in some sense is tied to that root t rate because of the way we have developed. Yes.
So is there any, so first I just want to clarify, the thinning procedure is not, it's not adaptive to the function you're going to use afterwards, right? In fact, it doesn't even talk about that function at all.
The only thing that it adapts is the like it uses the kernel.
Yeah.
Yeah.
Right,
So
which is
yeah.
a choice you make, perhaps informed by the function.
Yeah, so if you think of, so we thought about it, given a function, what is the optimal kernel? Back of the envelope calculation suggests that maybe the kernel should be kxy is equal to f of x times f of y.
Okay.
But that means you need order t function evaluation, so you are back to the original.
Sure.
To compute the 2t kernel evaluation. So I don't have a great answer other than that. Like it looks like if you only care about this function, use f of x times f of y. But then you're back to using t evaluations.
So my question was going to be, could you imagine something in between where, for example, you have your kernel, right, which isn't the actual function, and if you sort of first, maybe not thin a half, but like, if you imagine rather than selecting half, then a quarter, blah, 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 you go the other way, but you first select like 5 points, and then, then 15 and so on.
You mean build it rather than...
Yeah, could you interleave function evaluations with thinning?
That's a great question. I mean, and that is something I would be very happy to chat, like what would be a reasonable strategy.
Yeah, you should all.
So like one thing is like you can think, okay, what if I, thin and evaluate on the root t points from first thinning, and then can I change the kind? So that's, I mean, we are open, like we don't know.
All right, cool.
Potential.
It's very interesting.
Any?
So you really, you cannot insist on having, you fight against bias, right? You fight against bias and you want to convert fast. But in fact, you really sort of, if you want to make sure, with the forecast, to estimate the likelihood that the patient doesn't die, right? You really want to have an upper bound on something, right? So when you really don't, well, it's good to have a precise but you really care it's unbiased or not. You could be biased in the right direction, right?
Yeah, so I think you're asking like, so at least to my understanding, whenever clinical trials are involved, there is a confidence, there is an estimate, and then there is an interval around it. And you care whether the interval covers 0 or not, or is it like, that's one way to think about it. If it covers 0, then treatment is not effective, and if it is on the right side, then it's effective. If it's on the left side, you are really concerned, right? So your question is, but that interval has uncertainty in there. If you can make the uncertainty smaller, then you are making experiments cheaper to run, you know.
So I agree with all of that. I'm saying sort of not necessarily sort of to, you know, sort of thinking sort of, you know, in real time, it's not necessarily that it's unbiased, right?
No, I'm not talking about unbiasedness here. Like I was saying that given a quantity of interest, I want to build a confidence interval that is cheap to build. And getting a good, so the prior words, they will give you a cheap confidence interval, that is, you can build it quickly, but then it's wider. The question is, can you shrink without losing computation? That's the goal. And in the previous slide, I was saying sometimes you care about fixing the bias. That is something we're working on. So currently, if you don't care about the bias, this is good. Like, so yeah, so probably.
Okay. So just choosing points somehow reduces to choosing kernel functions evaluated on those points, right? In just x, instead of having xi, you have these new i's.
Yes.
And you work with new i's.
Yes.
How do you rank new i's?
Oh, so the goal was
the best ones.
the goal was that we want to estimate the mean, and so we want to estimate the mean. So instead of this, now we will use this. But we want to make sure that the quality of this estimate is as good as the original one. So we are giving this an implicit guarantee. So it's like, if you run our procedure, use just the output points, the fluctuation of that around the truth.
No, I'm talking about this Monte Carlo, this Markov chain that you showed, the value beta. How do you choose which sample you want to remove and which kernel functions you want to remove?
So the thing is, we are assuming you are given an MCMC point. So you have 1,000,000 points from the chain. Now, which of them do I keep is the output of our algorithm. That is literally the output of the algorithm. Whatever the algorithm outputs is where you query the function. Yeah.
So I'm asking about that algorithm. What's that?
Oh, that's what I was trying to show. Like, it's the recursive halving algorithm, and
Yeah. So my question is that this recursive halving will be implemented on functions v1, v2, vt.
yes. What are these v1, v2?
Is it difficult to build this implementation?
Oh no. So this is actually kx1 dot.
Yes, it's function.
Yeah. So that's the kernel function. So so to run the procedure, you only need to evaluate the kernels. So if you can evaluate the kernel, you can thin, like you can, yeah. So there is so when I say this, right?
So my question is that what is this norm, the absolute value?
So here you can think of it as the kernel norm, if that helps. But if you are in the Euclidean space, just think of thinning points. And you, like your functions you care about is only of the form beta transpose x. Suppose those are the functions you care about. Then this is the infinity norm on the points. So v's are exactly x. So to run the procedure, you maintain this running sum, and you choose the probability of choosing the next point. You change it from half depending on what the sign of this thing is. If it helps, you can think of it as the other way to interpret the algorithm is it looks at 2 points at a time and it picks one of them with higher probability, whichever one is more suited. So suiting is like measured. See?
Following Shane's question about the uncertainty quantification in the output,
Yes.
the fact that you are sort of doing this discrepancy at multiple stages, does it not mean you're getting multiple core sets, all of which are somehow independent and good?
So great.
Good.
I like. So they are not really independent. So that's the thing we were trying to work with. So you are right. This splitting, at each stage we get 2 equal halves, which are equally good. So after root and thinning, we actually have root and candidates. So the post-processing picks the best one, then does a probabilistic swap, some kind of swap with the original one. Yeah, but showing that these are, we thought they will be roughly independent, but it's hard to show it. I'm happy to chat if there is another.
I don't.
Yeah. No.
But if they were, you would answer Shane's.
Yeah.
Okay.
If it were, yeah, that's true. Yeah, and we want to give uncertainty estimates using the same number of evaluations, right? We don't want to pay. So I think there is a way, but we haven't. Now we only.
Can you summarize in 1 minute or less?
Yeah, let's see. 1 minute is a bit too much, but okay. Maybe 3 minutes. Give me 3 minutes to, it's just motivation, right? So this part of the talk was about inference or building AI agents for personalized treatments. And we are, I was working on these mobile health applications where your goal is to build these AI agents. Think of them as mobile apps that are trying to nudge you at the right time to be more active, okay? The long-term goal here again is to use these mobile health apps as, you know, some digital assistants that keep track of your health over time and then intervene and tell you now is the time to go to see a doctor. When you go see a doctor, doctor will look at the data that the app is generating to make a better decision. But that's again long-term, okay? So and these kind of apps are being developed by all kinds of, like Apple is interested, of course, because of the Apple Watch. But also the government, Veteran Affairs, is interested in developing these apps because it can reduce the cost of care. So a concrete example of a clinical trial in this space is, it was called personalized HeartSteps, where the population, it was a clinical trial run with Kaiser. You have hypertension stage 1 patients, they just diagnosed with hypertension, and if you can bring them on good healthy routine, they won't progress to stage 2, and they don't have to take a chronic treatment like some people. So this is like important if you can make them walk. The app is a bit more complicated, but one component of the app was sending nudges to go take a walk at pre-specified times, 5 times a day, okay? So now you can imagine if you send nudges too many times, how many of us actually pay attention to notifications? Very few, okay? Because if it is irrelevant and at random times, I'd rather just delete the app than or just turn off notifications, right? So it's kind of important to personalize these interventions. So here, the way you measure the outcome is they were using Fitbit, so 30-minute step count after decision time. And your goal, well, the real goal is something else, but you can think of it as, I want to intervene if it will actually improve the number of steps the user is going to take at that time. If not, I don't want to intervene. So that's what I want to work on. So given such a clinical trial data, and these apps are developed in many stages. So first they try something, then they iterate on it. And our goal is between trials, how do I inform what's going well, what's going wrong? So a simple question is, I have data, can I ask, did it work, right? And you can ask 2 questions, like 2 very simple questions. Was sending these nudges useful for a user? So we are talking about user. And was the algorithm useful? Like, did the algorithm send the nudges at the right time? And there are challenges because how does this nudge affect my brain? Who knows, right? Like, it's very complicated. And the data is collected adaptively, so there's feedbacks and you want to account for them. And these clinical trials are expensive. So it's hard to, like, it's not large sample regime. So the talk was about this. I also work on this, but we will not get into that. And just to summarize, this is the diagram I talked about, and I'm broadly interested in across these things with applications in healthcare. And just in case any of this is exciting, there are like some research. I mean, we have done research on all these things, and that's it. Anything that I presented today excites you, Roads 226, that's where I sit. Please drop by. That would be great. Or send an email. I can get.
We've already butchered you with questions, but if someone has burning, one more. Okay, then munchies. Thank you.
Thank you.